In the last video, we talked about electron configurations and how we write them. In this video, we will talk about electron configurations and how to relate them to the periodic table. There's a simple trick that we can do by using the periodic table that will let us know which electron configuration goes with what atom or what element. We can color code the periodic table in what is called blocks, which correspond to the different orbitals, the s block, the p block, and the d block. Elements that fall under these blocks or these columns, they are filling the s orbitals, the p or the d orbitals. They might be filling them in different principal quantum numbers, so different energy levels, but they correspond to a particular orbital. And we'll take a look in the next slide. The block in which the element is found then indicates the type of orbital that will be filled last in its electron configuration. We first start with the most recently completed noble gas core electrons, and then we count across the following period or row to determine the rest of the configuration. So if I have an element and I find it in the periodic table, I look to the very last column to see which noble gas comes before my element. That's going to be the shorthand notation. So I'm going to write that noble gas, and then I'm going to count off the rest of the electrons that are left, and those will be the electrons that are filling out last. So let's take a look. Here's the periodic table without any elements, but only showing the rows and the columns. You can see the rows don't change, so the first row corresponds to the first energy level. And since that energy level only has one sublevel and also one orbital, the first two elements in the periodic table are filling the 1s. Now I only have two elements in that first row because, as we said, each orbital can only hold 2 electrons. So here's hydrogen having 1 electron, and helium is also filling the 1s with a 1s2. Now helium is over here because it is a nonmetal, but really in the s block it would fall over here. Now if I'm looking at row 2, which are the elements that are filling the second energy level, remember that the second energy level has 2 sublevels, so it's got the S and the P. These first 2 columns are filling the 2S, whereas the last 6 columns are filling the 2P. So if the element falls right here, it is filling the 2s1 and the 2s2. Remember that the s orbital only holds 2 electrons. So once I've placed these 2 elements, then the s orbital is full. And now I move on to the p orbitals. So I'm filling the 2p1, p2, p3, and so on and so forth. The same thing is true with the third level. Note the difference when we get to the fourth level. This middle block here, even though it's in the fourth row or the fourth energy level, the d orbital is 1 less. So it's the 3d even though it's in the fourth level. This is the 4d even though it's in the fifth level. 5d in the sixth, 6d in the seventh, etc., etc. Now the f orbitals are down here, but we won't talk much about them really. Let's take a look at a sample problem. So write the ground state electron configuration using the noble gas core abbreviation for each of these. So I'm going to do the first one and then you can try the other two. First of all, we go to the periodic table. That's our friend. Now you can print this and have it for your records. It doesn't matter to me as long as you are able to figure out what the configuration is. I look for calcium, and that is this element over here. Once I find calcium, I look to see which is the noble gas that comes before row 4. It comes at the end of row 3, and that is argon. My noble gas then is going to be, so brackets, argon, close square brackets, and then I count what is left over, which is the 4s orbital. 4s1 is potassium and calcium is 4s2. So the shorthand or noble gas core abbreviation for calcium is going to be square bracket argon, close square bracket 4s2. Now you can try tellurium and bromine. Here's tellurium and here is bromine. Okay, let's continue talking about valence electrons. These become important because all the chemistry happens with valence electrons. We divide the electrons of any element really, into two different kinds, the core electrons and the valence electrons. The inner electrons that come, basically it's up to the previous noble gas, they are called core electrons. Those really don't participate in any chemistry. They're just there to fill up the space. The valence electrons are the electrons in the outermost area, the outermost shell. So the electrons with the highest principal quantum number, the highest row. Okay. Valence electrons are important because it gives the elements their personalities. Now you can figure out that the valence electrons configurations within the same groups are the same. So if I'm looking at group 2, for example, they all have the same configuration. The only thing that differs is the row. So beryllium is 2s2, magnesium is 3s2, calcium is 4s2 because they're found in row 2, 3, and 4 respectively. And I can go on. However, all of them have only 2 valence electrons. Those are the electrons that are found in the highest principal quantum number. And those are called valence electrons, very important in chemistry. Let's look at a sample problem. Identify the valence electrons for calcium, tellurium, and bromine. I did calcium last time, so I'm going to do tellurium in this problem, and then you can do calcium and bromine as just to try it out. So tellurium I find right over here, and tellurium is in row 5. Its electron configuration would be krypton, so square brackets, krypton, and then 5s2, the 4d10 right here in the middle, and then 5s or 5p, 1, 2, 3, 4. So tellurium has 5s2, 5p4 outer shell configuration, which means that since these electrons are in the highest energy level and value of 5, these will be the valence electrons, and I count 2 from the S and 4 from the P. That makes 6. So tellurium has 6 valence electrons. Now you can try calcium and bromine. And lastly, for this video, we're going to discuss Lewis dot symbols. These become useful to us as we look at the connectivity, how the elements connect to each other in a molecule, and then eventually we'll talk about the shapes of molecules as well. And they have influences in polarity, and we'll talk more about that when time comes. But for Lewis dot symbols, we distribute valence electrons as dots around the symbol of the element. So we first write the symbol, then we determine how many valence electrons that particular element has, and then we distribute them around the symbol. For the most part, now there are exceptions, the maximum number of dots around the element symbol is 8. We call it the octet rule. Octa meaning 8. So 8 valence electrons in total around the element symbol. It's 2 electrons in the s and 6 in the 3p orbitals, right? So 2 each. I have 3 of them for a total of 6. So 6 plus 2 gives me 8. Elements will beg, borrow, and steal to get 8 electrons around them. Now, they have some, and they can either give them away to form ions, or they can take the electron completely to form negative ions, or they can share the electrons to make 8 around them. But we're going to follow the octet rule, which means the elements prefer to have 8 electrons around them. Now, some can have fewer and some can have more than 8, but those are exceptions to the rule. The rule is 8 electrons. Now, when we write these Lewis dot symbols, we do not put a second dot in any position, top, bottom, left, or right, until there are single dots in each position. And then we go back and basically put a second dot in each of those to make eventually 8. But let's take a look at the periodic table and Lewis dot examples. Hydrogen has only 1 electron, and so that dot corresponds to the 1 electron of hydrogen. Helium, on the other hand, has 2, so helium would have 1 here and 1 here, really. Lithium has, remember, these are valence electrons. Even though lithium has 3 electrons total, 2 of them are core electrons because they correspond to the nearest or the previous noble gas. And so those are core electrons. And it has 1 valence electron. So note that each group has the same valence electron configuration. And so lithium, sodium, potassium, rubidium, etc., they all have 1 dot because they only have 1 valence electron. Right? This is 1s, this is 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. If we move to the second column, beryllium has 2 valence electrons, 1, 2. So we put those 2 dots on opposite sides. Okay? When we move to boron, it has 3 valence electrons, so we'll put 1, 2, 3. We space these out. Carbon has 4, 1, 2, 3, 4. And now that I have a dot in all the positions, I can go back and put second dots by each of these that I've already put down. So for nitrogen, I have 5 valence electrons. Well, I have to put the 5th one somewhere, so now I start making pairs of these dots. So nitrogen will have 2, and then 1 on so 2 on top. I mean, these don't have to be on top necessarily. They can be in any of the positions. But if I have a pair of 2 on the nitrogen, then in the other 3 positions, I will have single dots. For oxygen that has 6, it will have another one of those positions paired up. So I have 2 on the top, 2 on the bottom, and singles on the sides. Once again, this could be paired up here, and that could be single. It doesn't matter. What matters is that 2 of the positions will have 2 dots and 2 will have single. This, for the next group, fluorine will have 7 valence electrons, so it will have 3 positions paired up and 1 single. And then finally, neon has all of those, has 8 valence electrons, and they all are paired. Now you can see why the elements want 8 electrons around them, because that corresponds to the noble gas configuration, excluding helium. But the noble gas configuration is 8 electrons around the central atom, and since it's got what we call a full shell, full electronic shell, they are happy and non-reactive, and every other element is trying to get to this configuration, and they do that by either completely losing, completely gaining electrons, or sharing electrons. When we write Lewis dot symbols for molecules, we will follow certain rules, and here are the rules. We first add up all the valence electrons that each element participates. So if I have HCl, for example, hydrogen will bring in 1 electron, and chlorine, which is group 7, will bring 7 electrons. And so we have a total of 8 electrons to deal with. Those valence electrons, we will distribute them around all of the atoms. We add an electron for every negative charge, or we subtract an electron for every positive charge. So if I have an ion that has a positive charge, then I would have to subtract an electron, and vice versa. Then the least electronegative atom will, except hydrogen of course, will go in the middle. Now, we haven't really talked about electronegativity yet, but we can talk about the atom that has the more metallic character, so it lies more to the left or to the bottom, will go in the middle. Then we will distribute the other atoms around the central atom, and we will write bonds between each atom. And each bond, whether it's a single, double, or triple, but each bond contains 2 electrons. So if it's a single bond, it will have 2 electrons. If I have a double bond, it will be 4 total electrons that are being shared. And if it's a triple bond, there will be 6 total electrons that are being shared. But once I write those bonds, then I count off how many electrons are used in bonding, and I subtract them from the total number of valence electrons. Then we assign electrons to terminal atoms to try to satisfy octet rules, or for hydrogen, hydrogen only needs 2, and so hydrogen will only have 1 bond. But the rest of them, we distribute electrons as what we call lone pairs to terminal atoms, to atoms on the side, to form octet, so 8 electrons around and the atom, and then we subtract them from the total valence of electrons that we calculated. Then once we do that, if there are any leftover electrons, we assign those to the central atom. If the octet is not satisfied, we will form double or triple bonds until all of my atoms have satisfied the octet rule. Now there are exceptions to the octet rule. Phosphorus is one, and sulfur is another that we will be using. Phosphorus and sulfur can accommodate more than 8 electrons, and boron, B, is another that can accommodate fewer than 8. We will be working these problems in class. It is very difficult to actually draw these out while I'm doing a video. I have certain videos that I have done where I show you how to do some of these problems, and I will have them available for you, but we will be doing a lot of these Lewis dot structures in class.